Hey everyone, have you ever thought about why you'd weigh so much less on the moon even though you're still the same person? It's a super cool physics puzzle, and today we're going to solve it together with this one simple but seriously powerful formula. F equals m times g.
So, this is the big mystery, right? You step onto a scale on the moon, and suddenly the number is about 6 times smaller, but nothing about you has changed. How does that even work? Well, it's not magic, it's physics, and we're about to break down exactly why this happens. Let's think of this as the astronaut's riddle. And to solve any good riddle, you need clues. We need to find two essential pieces of the puzzle to figure this whole thing out. Let's start with the first one, which is all about what you're actually made of. Okay, so our first clue is something called mass, which we show with the letter M. Mass is basically just the amount of stuff, all the atoms and molecules that make you up. Now, here's the most important thing to get. Your mass never, ever changes. It doesn't matter if you're on Earth, on Mars, or just floating around in space. Your mass is always the same.
And this is a really, really key idea. Let's say we have this object, right? It's got a mass of 10 kilograms here on Earth. Now, if we could magically teleport it to the moon, guess what? Its mass is still 10 kilograms. The amount of stuff in it didn't change at all. So if your mass is always constant, that tells us something else must be at play here.
So that brings us to our second clue. If the stuff in you isn't changing, then the force that's acting on that stuff must be the thing that's different. And that brings us to that invisible force that runs the whole show, gravity. Our second clue is what we call gravitational acceleration, or just G for short. You can just think of G as how strong the pull of gravity is in a certain place. A huge planet like Earth has a really strong pull. A smaller body like the moon, its pull is a lot weaker. This is the piece of the puzzle that changes depending on where you are. And look at this chart. The difference is huge. Here on Earth, gravity's pull, or G, is 9.8. But on the moon, it's just 1.6. You can see the bar for Earth's gravity is way, way taller. In fact, it's about 6 times taller than the moon's. And that's no coincidence. It's the exact reason why you'd feel 6 times lighter. So there we have it. We have our two clues, a mass that never changes and a gravitational pull that's different depending on where you are. With these two pieces, we can finally crack the code and solve this weight mystery. So this is where it all clicks into place. We start with the amount of stuff in an object. It's constant mass, m.
And we factor in the local gravitational pull, g.
And boom, you multiply them together and you get the solution. F equals m times g. That F is what we call the weight force. So see, your weight isn't really how much stuff you are, it's the force of gravity pulling down on all that stuff. And since it's a force, we measure it in a unit called newtons.
Pretty cool, right?
Now that we have the key, we can actually use it. We can take this formula and calculate an object's weight basically anywhere in the universe, as long as we know its mass and the local gravity. Okay, let's look at this table and try it out with a 15-kilogram object. First thing you notice, the mass is 15 kilograms on Earth, and it's still 15 kilograms on the moon. It's constant. But on Earth, we multiply that 15 by 9.8, and we get a weight of 147 newtons. Now, take it to the moon. We multiply that same 15-kilogram mass by the much weaker gravity, just 1.6, and the weight is only 24 newtons. See? Same mass, but a totally different weight. And what's so cool about this formula is that it's not a one-trick pony. With a little bit of simple algebra, we can just rearrange it. That means if you know any two of the values, like force and mass, you can always figure out the third one. So, for example, what if you knew how much something weighed and you knew the local gravity, but you didn't know its mass? Well, you just shuffle the formula around. To get mass by itself, you just divide the force by gravity. So you get m equals F divided by g. Simple. Let's run the numbers with a quick problem. Say an object weighs 294 newtons right here on Earth, where we know g is 9.8. So we just plug those numbers in, 294 divided by 9.8, and that equals 30. That means the object's true mass is 30 kilograms. Just like that, we found a core property of the object. So there you have it. We've totally cracked the astronaut's riddle. Let's do a super quick recap of the most important things you should take away from all this. All right, if you remember anything, remember these 4 points. 1, your mass is the stuff you're made of, and it never, ever changes. 2, your weight isn't mass, it's the force of gravity pulling on it. 3, because gravity is different in different places, your weight changes. And 4, The beautiful, simple formula that ties it all together is F equals m times g. Okay, now it's your turn. We've used the formula to find weights and to find mass, but what about finding gravity itself? Here's a little challenge for you. Using what you just learned, can you figure out just how strong Jupiter's incredible gravity really is? Give it a shot, and thanks for joining me to solve the great weight mystery.